we live? Okay, I think we're live. I think we're live. Okay, hello everyone and welcome. This is the Traceback, and you can call me Trace. So, on this channel, we're going to pretty much focus on having fun programming. We will be exploring different projects in different languages, um, but from a first principles basis, right? It's more fun experimenting and seeing how things are built, and than like just jump into libraries and so it's more exploratory and yeah. So pretty much, as you can see in the top right hand corner, I have this controller that I have built, and I am I want to start programming it pretty much. So it is based on it was initially based on the Raspberry Pi Pico, and then I got a Pico W, and then I just got a Pico 2W, and so I decided to finally just put it together on a board that I had laying around, and yeah, so I intend to bring it up. Um, the first thing I wanted to get started with was the SPI bus. So under the screen, I have got two SPI not flash shift registers that are connected to these LEDs, and also to the reset pin of the LCD. And so I want to get that running first so I can get the LCD, and then that way it's, I guess, a lot more like visually interesting during the stream sessions. So yeah, I want to get started with that. So I guess I'd like to explain what I'm talking about. Just let me see if I'm right. So I just want to bring up the right, and okay, so let's just take a look here. So the 74HC595, I don't know if there's a shorter name to call it, but is a shift register, and it's a shift register is pretty much just um, a chip that holds some bits, right? In this case, 8 bits. You can chain these together, which is pretty convenient, and so I've chained two of them together to form a bank of 16. And how these work is, yeah, this is a pretty good animation that I found explaining the whole process. So pretty much what we're going to be doing is we have some data, right, which is 16 bits or 2 bytes that we want to write into our shift register, right? And so we will clock our data 1 bit at a time onto our data line, right? And then toggle our clock pin, and each time we toggle our clock pin, the data on the bus is read into the SPI register. So as you can see, we put our data on the bus, we toggle the clock, and the data is written into the shift register. Now, after the data is written into the shift register, it doesn't automatically show out at the output, right? And this is a great feature actually. So you could do that if you want to, but the way we have it set up is so that the data is not like reflected on the output while it's in transit, right? And so one once we have the data written into the shift register, um, we want to go ahead and I just realized you probably cannot see me. I will get that fixed in just a second. And I will bring that here. Okay, so yeah, so right, and so yeah, we are pretty much going to be toggling the data one bit at a time into the chip, and right, so this is pretty much the layout of the chip. As you can see, we've got 8 data pins. um, Most of these pins you can ignore. The ones we are really interested in is our um, the ones we are interested in is our data pin, and our clock pin, and also our this is our clock, and then I think this one is our latch, right? If I remember correctly. Yeah. Okay, come on. So yeah, so this is our latch, right? So we just have three. So we have our clock that we care about. We have our clock. Sorry, our latch. This, why is it called register clock? Anyways, it's called a latch. And then we have our clock, and we have our data, right? And so those are the three pins that we really care about. And so typically you could pretty much do that with let's say MicroPython. So yeah, let's go ahead. Right. So now, mic. So this microcontroller actually does have hardware dedicated SPI buses um, that we could use to power the to drive the shift registers, but unfortunately it only comes with two of them, and one of them is being used for the display and the other one is being used for the radio, which we'll get to in our future videos. And so we are going to be using some other pins, right? And yeah, so that brings us to the SPI interface here, right? So why do we need our own driver when MicroPython comes with an SPI implementation, as well as a version that doesn't require hardware, right? So as you can see, MicroPython also comes with a soft SPI class that allows you to pretty much let the CPU toggle the pins manually, right? So inside the Pico, let me see if I can pull up the data sheet. RP20-350 data sheet, right? And let's take a look. Okay, so right, so we are looking for the PIO. GPIO. Okay, so right. Don't know if this is big enough. Okay, so I actually haven't looked at this yet. Like I said, I was developing this on an RP2350, an RP2040, which is once again, I'm new to this, so I do apologize. Let's go ahead. Okay, there you go. Right, so I hope you can see. So yeah, I had an RP2040, and this is an RP2350, right? And so yeah, this is the initial board, and this is the board that we are developing for. So as you can see, our is there a better diagram? Okay, I'll just see if I can find are some diagrams. It's a bit hard to find now, but yeah, let's stick with this for now. But pretty much the CPU, right? The microcontroller has connections to all of the GPIOs, and all the GPIOs have special functions, right? That's what I was trying to find. IP2040 pinout. Let's see what we've got here. Okay, yeah, this is a good site that I like to. Right, so the Raspberry Pi Pico is set up in such a way that the CPU has a way to talk to all of these pins, right? So we can turn each pin on and off, right? But in addition to that, okay, so we could totally do that, right? And that is what this soft SPI flash does. But with the program that we're implementing, we want everything to be as asynchronous as possible, right? The CPU, as you can see, is going to have a lot of responsibility because it has to manage quite a few devices as well as communication. And so we are going to be doing a lot of cool, fun stuff with like multi-threading and async IO. And so one of the main reasons why I don't want to use soft SPI is because the Raspberry Pi Pico comes with something called PIO. PIO. So let's see if I can find that here. Yes, PIO. I hate it when it comes. Right. So let's see. PIO. Introduction. Right, so this is just the data sheet for the RP2350, which is the Raspberry Pi Pico 2, and inside it, it has something called a PIO, which stands for programmable IO, right? What that allows us to do is pretty neat, actually. So, right. So back to this diagram, right? So as you can see, all the pins are mapped to fixed functions, right? So GPIO 0 can either do UART or TX or UART RX. Sorry. So GPIO 0, for example, we can only do right. So with GPIO 0, we can pretty much only do like SPI 0 RX or I2C or UART, right? And like I was talking about, so we have SPI 0 and SPI 1, right? And the pins are pretty much spread out, which is pretty nice about the RP2040 compared to some other boards, right? But what happens if you use both of them, right? Again, you could do that with soft SPI, but I want to try something new, and this is what the stream is pretty much about. So the Raspberry Pi Pico comes with PIO, and it stands for programmable IO, right? It says the RP2350 contains 3 identical PIO blocks. Right. So, yeah, PIO is a versatile hardware interface and can support a variety of IO standards, including 8080, 8600, the I2C, I2S, SDIO, SPI, UART, VGA. I've even seen people do like HDMI and stuff now with the some of the new boards that are out. So you can do a lot of cool stuff with these state machines, right? And so these PIO are state machines. They have a limited set of instructions, and they can run special assembly instructions, right? They can move data from main memory into their FIFO or a scratch register and move that data onto a pin. They can move data between uh, pretty much any part of the board, right? From the CPU to the pins, from the pins to memory, from memory to the DMA controller, and anything in between. And so you've got a lot of like options with that. But we just want to try something fairly simple, right? We have right. So this is a good diagram, right? So our Raspberry Pi Pico connects into our state machine, right? Which pretty much has a few different elements. We have an output shift register, right? An input shift register. Okay, so I guess let me go over these one by one, right? So an output shift register pretty much um, takes data from our main memory and into our state machine, our PIO state machine, right? I know it's a bit confusing because it says out shift, but it's coming into our it's out of our main memory and into our PIO, right? Same thing with our RX, right? It's RX because we are receiving it in our main memory, right? And it's in shift over here because we are shifting data from somewhere else, like the pin, right, into our shift register, right? And it has a program counter that keeps track of where we are in our program, and a bit of control logic. It can also it has, I, I mean, the opcodes for the PIO state machines are pretty simple, and so you can, um, for instance, send instructions from like the DMA straight into the PIO and have it be interpreted as an instruction. And I do have plans to maybe try out uh, like a multi-threaded GPU kind of thing where a display driver, sorry, where we can like write to like different parts of the screen at the same time. And I think it'd be pretty cool. I actually have a cool implementation of like an async driver for that I can't wait to show you guys as well, right? So hopefully we get there one of these days. Right. So pretty much, PIO programs consist of uh, a set of instructions, right? And uh, directives, right? These instructions allow us to. Okay, there's some new instructions in the. I guess there's some new instructions in the RP2350 or the Pico 2. I'm just going to call it Pico and Pico 2, and I hope that is clear enough to everyone. Let's see. Okay. So, all right. So let's go on. Sorry about that. So, um, right. We are looking at the C API. Um, I do want to come back and rewrite everything in C, but I think it is going to be a lot more interesting to a lot more people in Python because I think right now Python is pretty popular, and also Python and microcontrollers is pretty cool. But the Raspberry Pi Pico does have a built-in async system, which I think is pretty neat as well, and we will get to get that, and maybe one day we'll do like some kind of like benchmark between the MicroPython async implementation and or try and port the MicroPython async implementation to the no, sorry, rather the C implementation of async into MicroPython. Okay, so um, I am just trying to find the instructions, and I wish there was a C. Okay, right. So this is a summary of our instructions. We have got jump wait, in, out, push, move, pull, move. Why do we have two moves? And three moves. Okay, I guess we could move. Okay, I guess some of the new instructions we're talking about, and IRQ and set, and yep. So these are the encodings. We don't need to get into any of that because we're going to be working in MicroPython, right? And so MicroPython, I believe, has implementation for an interface for, right? So okay, for the state machines, and also I feel like we should have some instructions. Okay, all right, let's see here. Okay, right, so here we have our instructions for our PIO, and there's quite a few instructions, but they're not that many, and so it should be fairly straightforward, right? Let me see. How does SPI work? Okay, let's see if we can find like a simple explainer for SPI. So this is pretty much the protocol that we are going to be implementing, right? Right, we modulate our clock, and we put data onto our data bus, and it gets clocked into our peripheral. Okay, so actually, let me see. P20 SPI example. There is an example in there's an example PIO. I know there are SPI. Yeah, there you go. No, not this. SPI, PIO. Let's see. Let me see. PIO. Okay, yeah, here we go. Here there's an example of an implementation, right? So we are gonna be pretty much doing something similar, except I actually noticed our SPI chips are only output, and so we don't really care about the inputs, and so we want to implement all of that. So our plan is to write a simple PIO program, right? Kind of like this, that we can just write our data into, and it just configures our LEDs for us, right? And that is the plan. So we can go ahead and get started. I will put this away. Okay, and we can get started. Let's see. Okay, so let's say define. Okay, I guess. Right, so we could say, let's call it SPI. Let's see, 7 shift range. Yeah, there's nothing harder than naming, right? So, what is this decorator? So there's a whole bunch of options here that we can use to create. Okay, so I'll shift direction, auto pull, pull thresh. Okay, so we have 2 banks, so we're going to change that. Auto push, no, we do not want that, and we do not want to push any data, right? Site set in it, right? So, right, let me look at the configuration. So we need our pin, so we need a clock, we need our data, right? And then we need our what do we call that, latch, right? Let's just call that CS, and that stands for chip select, right? So I have mapped those pins out somewhere. So this is a register, a driver for the shift register that I wrote, and okay, I just want to grab E here and just paste that there. So our clock is going to be pin 8, our TX or multi is going to be pin 6, and our chip select is going to be pin 7, right? Now there's some caveats that I didn't know before I started, or when I was making the board, right? For PIO, you do need the pins to be consecutive, and so because that kind of like you can't like instructions are limited, and so each pin is relative from a certain offset, right? And so it's hard to address pins that are not consecutive, right? You can with the side set, we can address up to 5 pins at the same time. So I was really hoping to take advantage of that, but we'll see. Excuse me. I am out of tea. So. Okay, so we gotta import IP2. Okay. So where were we? Side set in it. So we have 2 pins that we will use as side set. So with our SPI, we can we have to vary our clock signal while we put our data on the line. So we will be setting our data pin, and then so there's a lot of details that I'm leaving out of the PIO, and maybe as we go further I'll explain more, but each PIO instruction takes exactly 1 clock cycle, right? You can set the frequency of the state machine and determine the timings, right? So each clock each cycle takes 1 second. Each instruction takes 1 cycle, sorry. And so if you could only set 1 pin, that means you could only do 1 pin at a time, and so you wouldn't be able to set multiple pins simultaneously, right? And so with the side set instruction, right? I don't know if you can find that. The side, okay. It is used to control side set pin values. So the side set pins are pretty much pins which we can set at the same time we set our main pins, right? So let's see, side set. Side set. Come on. Side set. Okay, this sucks. Okay, side sets. Side set of value, blah blah blah. Oh my god, where's can we find anything? It's in there somewhere, believe me. Yeah, we'll find it. But it allows us to set pretty much, like in the our docs over here. Side set is to set side modifiers, right? So, right, let's go back to code, right? So, with the way we have it set up, so this is first, this is 7. So our chip select will be our first pin, and our clock will be our next pin, right? So we also want our clock to be low when we are idle, and our data pin should be low when we are idle as well. Okay. All right. So, right, what are we going to be doing? We are going to be reading 16 bits at a time from our TX50 into our shift register, and shifting them out, right? So we can start with let's go back with pull, right? And we can take a look at the docs again, which we have over here. We'll find that. Pull, right? So pull data from our TX50 into our OSR, and our OSR stands for output shift register, right? And so we want to wait until we have data right, and we have the right number of bits. So we gotta use that, right? So let's get rid of that, and we can say pull if empty, and I wish I had some kind of highlighting. That suck. Ouch. Okay, so and I said let's block until we have some data, right? And at the same time, yeah, I'd say that's pretty much what we want to do. So, right, so we could if we do wanted to have programmable frame sizes, we could start by setting like the Y register that we can use to as a counter, right? So we need somewhere to count how many bits we've shifted so far. So we are going to move into our X register 16, right? Um, okay, so actually, you know what? Let's do move Y. Let's move. Yeah, actually, you know what? Let's just save the instructions. So and hard code this for now. So we pull, right, and then we move our data here. We move our count, right? And I should, you know, let's one line at a time, right? So we move our data, we move our counter into a register, and then what do? We want to our clock line, so to read data from TX5416 bits at a time, and then here we are going to be updating our update counter, and then next right, we need to create some kind of, so let's call this label, right? And we can just say like loop, right? And then what we want to do is first shift out our data onto our pins, right? Let's take a look at the out instruction and how many, right? We have to set how many bits we want to shift in that cycle. So we say we want to shift 1 bit onto our pin, and right, and then next we want to toggle our clock, right? So we could so yeah, so now our so over here our clock is low, CS is low and our clock is low. Over here CS low, clock low. So also we can keep track of and right, and same thing here, right? Right, this is annoying. You need like a proper editor for PIO, because this ain't Keith. Right. Okay, let's go on. So once you put our data onto the line, I don't know if we can immediately transition, right? So instead, okay, let's go here And then now we want to pulse. So let's see that side. We want to, so our chip select and our clock, right? So we want to send our clock high, so that is our first bit, right? So like we got, let me just make this here so it's, I hope it makes a bit more sense what I'm doing. So we have our clock and our latch, right? And we want to set those, we can set up to 5 pins at the same time with this site set instructions. And the way we do that is by writing the value we want the pins to have with this instruction, right? And so for example, now that we have 2 pins, if each is 0 0, we have clock and then we could have 0 1 and doesn't show you my camera, and I think that might be going off any moment. You know what? I will just finish this up super quick. I'll take a break, come back, and we will get to testing. Okay. So, yeah, 0x. Let's just make that clear. Right, so CS low, and then our clock high, and OX. So 2, which will have our CS high, clock low, and then lastly, and have our X 3. It should be CS high and our clock high. Okay, I hope that makes sense. So that is what we're doing here with this site set, right? So our clock is going high, and our chip select is remaining low, right? Okay, so we want to do that. Let me just see what I can do about these. Okay, so now we have this here. Now I'm not sure exactly how long we have to hold this signal for, but we can just add a delay on, and then we can jump. How do you spell that? Right, I think it's jump. And jump and decrement X. And we want to jump to our loop, and we want to set our side pin back down to 0. Right? Okay, now. Right. Okay, so we come back here. We put the data on our data line. We toggle our clock down here. So we're doing this twice. And so I think when we're doing this here, we can do this here. So, right. Okay. So that each part takes equally as long, you know what I mean? And then, because this is one cycle, a low, 1, 2, because let's say we come here from one cycle, a low, 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 1, 2, high, 1 low, and then 1 low. So yep, and then finally we can like wrap to, we can set here as wrap target, right? And I think that's how we do that. Okay, so I think this is the basic implementation that we need to get started, maybe write some tests. Like I said, my coffee is almost out, so I will go grab a cup of coffee and I will be right back. All right, I will see you soon.